All right, so what we're going to look at are revision questions from last year's exam paper. That's what people normally want from me in this last week. So I've got the exam papers on the web page from 2009. There was no paper set in 2010 because the unit didn't run then. It runs every 2 years from now on. So you can download the papers and have a go at them. Alright, so let's just go through this. It's a 3-hour exam, closed book, no calculators. You shouldn't need a calculator. If you do, there's something wrong. And what I'll do is just go through these questions, and your exam this year is a little bit different. It does have 4 questions, but the questions aren't the same format as these questions, but they cover similar material. One of the reasons it's a bit different is you had a different version of 3073 as a prerequisite than the people that did this exam, and that means it needs to be a slightly different emphasis. All right, so what we do in question 1 here is ask you some fairly general questions. So you've done a number of labs, and what these questions are targeting is your understanding of the concepts in those labs. And a lot of the questions in the exam will be based around you understanding what's happened in the lab. So you've been quizzed on that already through Muso or Blackboard, but these are more your opportunity to explain things. So interrupt latency is important, and the measurement of that involves a crow triggering off the interrupt and another crow channel measuring the response as you've done in the lab. So the important thing to describe is how it's measured, which involves an oscilloscope. Now, you might ask, well, could you do this with other mechanisms? Could you do it in a software sense? And the answer is no, you can't reliably do that because of the way the interrupts are structured in the real-time kernel. So you only have a 1 millisecond resolution of the interrupts typically, and here we really need this down to microsecond type precision. So that's why you normally do it in a hardware measurement. So why is it important to measure interrupt latency? So give examples. You notice there's plural here on the example, so one example is not enough. Minor detail, but the way we mark these things, it looks for 2 examples in the marking scheme. So the response time is important, so a good example of that is this power electronic converter or inverter circuit where you're driving transistors with responses to interrupts. So you might have a interrupt mechanism that then has to send out control actions. So the latency then is very important for the performance of that system, and it dictates the maximum frequency of operation. So in the lab you've used optical shaft encoders, and the latency there limits the maximum speed. So that's pretty straightforward. So maybe I should get you guys to answer some of these questions because I'm not clear on how much you know. So why don't I get some people to volunteer some answers? So if you've got a NEOS processor, what factors affect the interrupt latency? Can anyone comment on that? There's several options you can select, and they involve software and hardware. What are they? Yes, so in the software, it's got to make a decision where the interrupt source is. I mean, there's IRQ 0 up to 7, I think, on the processor. Now, that can be done in software, which happens as a default, but you can, when you instantiate the processor, you can incorporate an interrupt controller that does that in hardware. So then it only takes, effectively one clock cycle to make that decision rather than a dozen instructions that you currently see. The other effect is the processor itself. So you have a pipeline or a cache available in the processor. So these are the other factors that you need to consider. And in the software, in the interrupt service routine, the number of registers you use dictate how many registers you need to save, obviously. So if you limit the number of registers used, it means that the interrupt can run much quicker. So that's another factor in all of this. So I've covered this point. So the processor type is important. Okay, so the Avalon bus you've dealt with several times in the labs, and the structure of that is centered around the address bus, which is 32 bits, data also 32 bits, and then the control signals. You've got the read, write, bus enable, acknowledge, and the IRQ. And then what else? Well, we'll look at some more examples in a moment. So with a multi-master bus system, what do we need to see in the implementation of a multi-master? Well, firstly, what is a multi-master bus system? Can anyone suggest a good answer to that? Yeah.
You might have a CPU and you might have something else that needs to write into memory separately.
So what's a good example of that? Another device. Yes, so an optical drive will use a DMA controller, for example. So it has direct memory access. And another example is an accelerator design that we looked at in lectures. So with an accelerator, the processing hardware needs direct access to devices on the bus without going through the processor. All right, so what support is typically provided by the bus design, so that involves hardware here, to enable this to happen? Now, you guys have used this in the lab. You've designed one of these things. What is it?
Arbitration.
Yes, an arbitration circuit is the answer. Okay, so arbitration logic is required to allocate the bus to one and only one master at any given time. Right, good. All right, so direct memory access needs definition here. Oops. So this is where the bus can be taken over for read-write bus cycles without involving the CPU. Now the idea is to speed up these transfers, because with a CPU you've got to load an instruction from memory and then execute that instruction, which is perhaps the memory transfer. But the DMA will not need to fetch instructions. It just goes through a sequence of actions based on its registers. So the registers in a DMA are the address, so you need to increment or decrement the address, and the number of bytes or words that you need to transfer. And then you've got to implement a control circuit to do that. Now you guys should be able to actually sit down and design with Verilog a DMA controller, and that's one of the labs that I considered, but we didn't have time to do that. It is not that difficult. So, list the steps taken by software when using a DMA controller. Okay, so how would you do this? What are the things you need to do? Well, you look at the answer to the previous question, you say you have to set up the address register, with a write operation, the number of words you need to set up, and then you've got to wait for the action to finish. So how is that done? What's a good way to do that? Can anyone suggest different alternatives? So you're sitting in the lab, you've got your DMA controller running. The software has to determine when it's finished. How does it do that? You've got two answers. Yes, you've got an acknowledged signal. So what do you do with that? Yep, so you poll that, do you? Okay. So you sit there in a tight loop, say, are you ready? Are you finished? Are you finished? Are you continuously? Well, that's a valid answer. That's fine. Got any other answers? What's a better way of doing it? Yeah, you connect it up to an interrupt. You connect it to IRQ 10 and then you write an ISR that handles all this stuff. And that may signal another process if you have a real-time kernel. So that's what's written here. A more efficient approach is where you service it with an interrupt service routine and then you may signal a semaphore that wakes up a process that is using that DMA controller. So that's the event-driven strategy, which we want you to understand as an efficient way to do things. Okay, can anyone tell me the difference between an asynchronous and a synchronous bus and how are they separated in the way they operate? How are they different? It's not a hard question, but you need to know the answer. So what's the word you're looking for? What's the big difference? If I give you an asynchronous logic circuit, it might be an RS latch, and I give you a synchronous one, it might be a counter. What's the difference between them fundamentally?
The synchronous one changes clock pulses.
Yes. So you have a clock in the synchronous one dictating when things happen, and the asynchronous you don't. So you have a system clock and things are, the control actions occur on clock edges basically. But in an asynchronous one, you don't have a clock. So things are potentially more efficient because you don't have to wait for an integer number of clock periods for things to happen. So you can have a 4-cycle handshake, for example, to interface to a memory, and that memory may have an access time that depends on the data that it's fetching. Depends where it is in the address space. And the Motorola 68000 used an asynchronous bus as a way of speeding things up. So in a transaction, which is in the next question, you need to account for variable response times. So some devices are slower than others. Now you've effectively done this in the lab by looking at the ready line on the Avalon bus. So in this timing diagram, what you're waiting for is this ready signal to go high again. And that's driven by the slave, the guy that's actually being accessed on the bus system. So here we have an example of a read operation. So the read-write bar is high. And that transaction is completed on the clock edge following the ready going high. So this clock edge here is when that completes. So you sample the ready line, you know it's finished, and then you can start a new transaction. And the write operation is similar. So you remove the write data, it can go high impedance after the ready is finished. Okay, so in an asynchronous bus, then you need effectively a ready signal that is driven by the slave that can happen at any time. It can finish at any time. And there's no clock to dictate when it's sampled. So the difference between cooperative and preemptive real-time operating systems. So in cooperative systems, the task switching can only occur when? So the possibilities are on an interrupt, when you allow it to happen, or when the operating system wants you to do it.
Is it when it's like in time, the task's like waiting in a time delay or blocked by a semaphore?
Yes, almost. It's a bit more general than that though. So in cooperative, it's up to the users to give up the processor. So they have to call a kernel function, and that's the only time you can get a context switch. Now the advantage of that is you don't have to worry about storing your context as carefully. So for example, you can make sure that only happens when all the registers aren't being used, so you don't have to save all the registers of the processor, for example. So that you can get a much more efficient context switch because it happens only when you allow it to happen. So the preemptive one is more responsive because it can happen any time, but you need to be more careful about the context or the registers of the processor. So that happens in response to an interrupt, typically, in all real-time kernels. So here is something a bit more concrete. Suppose a high-priority task is blocked when the low-priority task is running, and then you get an interrupt occurring. So here's the timing diagram of the cooperative. What you see happen is low priority comes along, you get an interrupt. The interrupt service routine will run and then returns to where it was running. And it's not until here that the low priority task calls an operating system function, which can then cause a task switch. So how is that going to be different in the preemptive case? Yes, so as soon as the IRQ finishes, you go straight to the high priority task. That's the difference. Okay. All right, so that's pretty easy. I'll just revert to this copy because it's a bit clearer. You should recognise this problem. You've got a CNC machine and an XY position on a table with DC motors like the pendulum and optical shaft encoders. So you've got these shaft encoders interfaced using PIO module. So you've got two of these things, so they're generating 4 outputs, phase A, phase B of each. And we've labelled them ABX, AX, BX, AY, VY. So you want to process the angular positions using 2 PIO modules, one for each axis. Right. So how would you configure the PIO module? So we've got a data sheet here that you can look at. So this is checking that you've done the lab pretty much. So what are the settings you would choose here? Just spit them out. Just blurt them out. So you want an input port, yes. Yep. Where is it? Oh, it's further down. So let's look at what's here first. So what about the width? 2, yeah. And input, and you've told me the mode, and if you look further down you want edge capture. So you want either edge, good, okay. So you need an interrupt on the edge. So that's this option here. Okay. So when you write to register 3, I think it is, it'll clear the edge that you captured. So when you enter the interrupt service routine, you've got to do that. Otherwise, the interrupts are still there when you leave. So that's, I'll just put this up so that we... All right, so we've got all that right. And just go up a bit. Now what's going on here? This enables you to clear individual bits as well. So you don't need that facility. You want to clear the whole lot and after you've read it. So here is the registers available to you. You've got the data, the direction, interrupt mask and edge capture. All right, so you want to write initialization code for the PIO. All right, so we're assuming we've got these global variables, the position of X and Y, and a context which is going to be used by the interrupt service routine. So here are the things you need to worry about, and the exact syntax is not important, but each line is. So you want to initialize the global variables, and you want to clear any pending interrupts that may be present on those PIOs. So that's both X and Y. So Y is further down. And then you need to load an interrupt service routine address for a particular interrupt request line. Okay, so that's done with this alt IRQ register. And then you need to enable the edge capture so that you then generate interrupts. So that's done with this 3, which is putting 2 1s in the least significant 2 bits, and that enables those to generate interrupts on transitions. And you do the same for the Y register. Okay, so that should be pretty easy, hopefully. And then you're asked to write the interrupt service routine that looks after the x-axis. And you're assuming you've got a system H file, blah, blah, blah. So that's good. Now what I've given you in the exam is this example code, so you can actually look up the syntax for things you may have forgotten. So that's available to you. And for example, the alt IRQ register function, you can't possibly remember the parameter order and so on for that. So that's why I've included it. So here is the answer that you're working on in the lab, and you would have done this already, so it should be pretty straightforward. So we've got the interrupt service routine defined as a static, which you need because it's generated from an interrupt. You read the value from the base, so that's the data. So that's the values the A and B. And then the edge register is also loaded here. So these are the signals that have changed. So if the least significant bit is set on the edge register, we know that A has changed and we're sending a value to this function call. And similarly with the other bit. You notice you check both signals because both could actually change by the time you get to the interrupt service routine. You don't assume that only one input change is generating the interrupt. And finally, once we've processed that, you then need to clear the interrupt source. Otherwise, it will just re-interrupt once you return from the interrupt service routine. So you remember from hopefully your experience in the lab, you need to do the exclusive OR function of the values. So if A has changed, then you increment if that's true. So that's the exclusive OR operation. And it's the other way around for the b-axis. So you decrement if the exclusive OR of the two is true. Yes. All right, any questions on that? No, that's good. So here is a bus timing question with a load word instruction. So we've got a 32-bit Avalon bus bridge with an 8-bit SRAM. So this is similar to your lab test actually, similar but not exactly the same. The reason it's slightly different is you had an 8-bit Avalon bus bridge with a 16-bit SRAM. So what we would like to do is to sketch the timing when we do a load into R7 of the address given by R2 plus 8. So you're given the contents of those registers. So you've got this value is going to be loaded into R7 after the instruction. So that's what's in memory at the address that we're looking at. And our address is F0. So once you add 8 onto that, you end up with F8 as the address. Okay, so here are all the signals that we need to worry about. So this is a read operation, so you have to understand that. So we've got F8 coming out on the address bus through the Avalon bus bridge, and the bus enable will be set just before a clock edge, and then we set the read action. So that's done by the Avalon bus bridge itself. And similarly, this is set by the Avalon bus bridge. So all bytes of the whole 32-bit word are active in this transaction. So read data is then something we need to drive, and that's done byte by byte. So you'll notice that we read at location F8 first, and that will return from the memory 7/8. That's the most significant byte. Yeah, I think the ordering, you have to worry about whether the least significant byte goes at the lower address or is it the other way around, big endian and little endian. So this is assuming a big endian protocol. So we read out the numbers and they get added to the appropriate place in the read data. And that place is determined by this stage. So we have to go through 4 bytes, so this just increments 0 up to 3. And you use that number to address where to load the data into this temporary storage register that's actually accumulating the 32 bits. And finally, at the end, we then capture the value into the processor at that point there, so when the acknowledge goes high. So you can follow that carefully. So what is an arbitration or an arbitration circuit? So we talked about that. You need them for bus access, mutually exclusive access. So you have an integer number of requests and the same number of acknowledges, where only one is asserted at any one time. So the other thing you need to worry about is if you're using an arbiter, you can assert the request line, but you can't drop it until you get the acknowledge. So you can't drop it and give up. So it's like ordering a pizza and then you tell the guy that delivers the pizza, "Oh, I changed my mind, I don't want the pizza anymore." You can't do that. So the assumptions are that you actually follow through on a request. So 3 different arbitration policies. Fixed priority. So you just pick out the highest priority request that's pending. What are the other 2? What are 2 others? Yep, round robin. So what's that involve? Yeah, so the priority rotates. And what's another one? You did this with Freddie, so just checking you've done it. What's the fairest arbitration policy? If you had an ideal world, what would be the fairest way to do that? And by fairest, I mean what will minimise the standard deviation of the waiting times. So let's say you guys want to go to the pizza restaurant yourselves, you want to buy a pizza. So you're the request. You arrive at the pizza shop and there's all these other people arriving at different times. What's the fairest way to give out the pizzas? Yeah, first come, first serve. You can actually prove that minimises the variance of the waiting times. But it's actually quite hard to design a first come, first served arbiter in hardware because you've got to store the order of arrival of all the requests. Well, fixed priority you don't have to. Okay, so that's all there actually. So round robin's a good compromise between the two, and it's quite popular in practice. You'll find a lot of bus systems use that. So the input-output behaviour, I just talked about that. We're talking about a synchronous case here. So we've got this clock line coming in. So in the synchronous case, what happens is all the requests get synchronised, so you only look at them on the rising clock edge, you make a decision, and then you assert one of the acknowledge lines on the output. And once you've had your acknowledge, you can then drop your request line. Now, I think Freddie would have gone over an example of how that works in practice with a timing diagram. Remember that? So that is embedded in that timing diagram. So you need to be mindful of that protocol where you can't drop a request until you've got the acknowledge. So you should be able to draw a timing diagram for each of those different protocols of arbitration policies. So an arbitration circuit can fail due to metastable failure, and this is a general question. So in a general case, you have a flip-flop where the output lingers between the logic states and resolves after an unbounded decision time, which is unknown. You can't bound that. So you need to allow a settling time for that to resolve in practice. So if you look at a digital circuit and you want to analyse whether it's susceptible to metastable failure, you need to be able to identify two scenarios for it to be vulnerable to metastability. One is where the output resolves to one state and the other resolves to a different state. So they're, say, 0 or 1 outputs as examples. But you also have to have a continuum of possibilities between them. So that could be the timing of two request arrivals. If they can vary continuously between those two possibilities, then somewhere between them is an unstable equilibrium point. So that can be proved with continuity theory in mathematics, in topology actually, that state will exist. So that means it's an unavoidable problem, and given that we've got a discrete output with continuously variable inputs, you can't get a perfect hardware solution to that problem. So here is another question on this. Complete a timing diagram for this synchronous arbitration circuit and show these scenarios and the metastable failures. So what we have is request 1 occurring before request 2, and the acknowledge goes to request, they're occurring at the same time here, and acknowledge 1 gets the resource and acknowledge 2 misses out on that clock cycle. And the second example, scenario 2, is where acknowledge 2 gets the resource due to the fact that the request 1 occurred after the clock edge. So that might be a fixed priority arbitration circuit in action. And the metastable case is where, request 2 comes in early, so it's looking like request 2 is going to get the resource, but then right at the last minute on the clock edge, request 1 comes along and attempts to request the resource. So it's just as you're shutting the gates on the ferry and you get this last passenger come along, and the metastable failure is the gate crushes the passenger's leg. And that's the discontinuous output. Right, so that's a nice illustration. Right, question 4 is pretty straightforward. It's about data acquisition systems, which we've just dealt with. So what's a transducer? Well, it's just an energy converter, actually. We've done all this stuff. These comments, by the way, are for myself, because what happens is we set an exam paper, and just to test it out, I will solve the exam paper and time how long it takes me to do it, and then multiply by 3, and that's got to be less than 3 hours. And if there's problems, then I'll write comments. If I don't understand my own question or someone else doesn't, then they'll tell me to fix things. So here we've got 3 characteristics: linearity, sensitivity, specificity, and they're defined there, and you'll find them in your notes. So a PID controller, you should be quite familiar with that at the moment. You've got the integral term, the proportional term, and the differential term. So you should know what they do. So the basic controller will be a proportional feedback, and that has a steady state error if you look at most systems, and the integral control will eliminate that after integrating the error for a short time, hopefully. So in the pendulum, you'll find if the disk lags behind the pendulum, which it tends to under proportional control, so it's behind in one direction and then behind in the other direction, the integral control should make it catch up after a short time. So say halfway across the swing, it should catch up, because this term gets larger and larger and eventually pushes the motor ahead in that direction. Now the problem is that you can get overshoot through applying too much integral control, and the differential control will look at the rate of change of the error. If it's getting too rapidly increasing it, then we'll back off the motor voltage effectively before it overshoots, so predicting where the error is heading. So that's meant to be described in these answers here. So the discrete version, you need to factor in a sample time, delta t, which doesn't affect the proportional gain, but if you're mapping from a continuous time to discrete time, then you've got to multiply the continuous time by delta t, and also you divide the differential one by delta t to end up with the discrete time version. So when you're looking at the Nichols, what's it called? The Ziegler-Nichols technique, you've got to convert continuous to discrete time via these transformations. So how do you choose the sample rate? Well, you obviously want the sample time to be much shorter than the response time of the motor. You want this controller to be able to act quicker than the motor acts, otherwise it's not going to be very good. So the time constant of the motor is typically, might be 1/10 of a second, so this guy has to be much shorter than, say, 100 milliseconds. So if you end up with a sample frequency that's too large, you end up winding up the integral control, because you're doing so many samples that this summation becomes enormous. And that can, because you can imagine the motor's not responding because you've got this time constant, say 100 milliseconds, and if you're sampling at 1 millisecond, then you've got 100 samples before the poor old motor can turn around the response. So you end up with this 100 times the error in the integral wind-up, effectively. And the other problem is if you take the difference in error between one sample and the next, it's usually going to be 0 because the motor's not moving. So the differential error becomes ineffectual. You just get this occasional 1 pop out and then it's 0 for the rest of the time. So the sample rate needs to be a compromise between these two effects, basically. All right, so now you had a lecture by Michael Zanieri on testing of commercial products, and he went through a whole lot of different test procedures. So there was heat cycling, where you put the device in an oven and you heat it up and you cool it down 100 times, and you check that the circuit board doesn't crack and all sorts of other issues that can arise with thermal stress. The other one is you apply 6 volts to your 5 volt power supply. Well, that's probably a bit, it's usually 10% is the tolerance. And you get a sandblasting machine out and you harass the equipment with that. And finally, you go down to the high voltage lab and you turn on the Tesla coil and hope that your Faraday cage that you're sitting in is particularly good on that day. So EMI is another one. So you get your mobile phone out. No, you don't do that. You actually put it in a controlled anechoic chamber, or you go out into a field on the outskirts of Melbourne where there's no mobile phone coverage, and you can then test the electromagnetic interference properties because there's nothing around and you can get a controlled environment. Vibration's another one. You need to drop your device from 1 metre onto a concrete floor, and that's a drop test. So anyway, to get full marks in this question, you need to have a sensible discussion. You don't have to cover every point, but you've got to show enough knowledge and common sense to describe these things. I mean, I can't give an exact marking scheme, obviously, but that's the sort of thing we're looking for. So as I said, your exam this year is similar in content, but because you've had less experience with real-time systems, then some of the questions are at a lower level, I guess, than this exam paper. So, for example, there will be some questions on how semaphores operate in a practical setting, this sort of thing. And similar things. So I think there's one question where you're given C code and you're asked to describe how that will perform or what actions will occur under some conditions. So you've got to actually understand how real-time code will operate, how it runs. Yes. Any questions about anything? The labs or your exam? I will put consultation times up on the website so you can come along with questions. I don't know when your exam is, but I think it's towards the end of the exam period. So that's probably going to be a low priority initially for you. Yes?
Is this the only part of the exam?
No, there's another one. There's 2008 as well.
Do you also upload the solutions?
No, I'm not allowed to do that. But you can... Actually, I think there's a... I'm not sure. There might be a recorded lecture that discusses 2008. I'll have a look. So you might be able to listen to that with fast forward. All right, so that'll do today. And on Thursday morning, Waiho Lee is coming along to give you a guest lecture, mainly about the Bionic Eye project, and he's promised he'll attempt a demonstration in the lecture. Yes.
So all the guest lectures are examinable?
Yes, they are. Yeah, within reason. I mean, it's not going to be the nth degree of detail, but yeah, in general terms, they are examinable. We're trying to build up your experience of embedded systems through those guest lectures. So they're different problems entirely. So it's good to get a different range of experiences. Okay, thank you, and we'll see you in the lab.